Swayam Prabha. Digital India. Educated India.
Namaskar. So, today we are coming towards the end of our course, and today we will discuss about the force current analogy, and then we will try to solve the analogous system, and we will see how the analogous system can be equally represented with the help of electrical circuit. So, let us start the today's discussion. So, first we will see what is the force current analogy. So, the force current analogy means the mathematical equation of the translation mechanical system are compared with the nodal equations of the electrical system. Now, consider the following electrical system which is shown in the figure. Now, this circuit consists of current source, resistor, inductor and capacitor. So, all are connected in parallel. So, in this case the nodal equation you can write as the current I is nothing but equal to V by R plus the current flowing through inductor, that is 1 upon L integral V dt, plus the current flowing through capacitor, that is C dV by dt. Now, if we substitute V with d phi by dt, or let us rather say d psi by dt, which is nothing but the magnetic flux. So, what we can write, I will be equal to 1 upon d psi by dt plus 1 by L psi plus C d 2 psi by dt 2. Now, if you rearrange, I will be equal to C d 2 psi by dt 2 plus 1 by R d psi by dt plus 1 by L psi. Now, the force balance equation for translational mechanical system we derived yesterday in the class, that we shown that the force F is equal to m d 2 x by dt 2 plus b dx by dt plus k x. Now, if you compare these two equations, what we get? We will get the analogous quantities of the translational mechanical system and the electrical system. So, if you see these two equations, you can say that force and current has the analogy. M, that is mass, is analogous to C, B is analogous to 1 by R, K is analogous to 1 by L, X is analogous to psi, and you can also say dx by dt, that is velocity V is analogous to d psi by dt, that is nothing but voltage V. So, this is what we have compiled in the form of table. Force F is analogous to current, mass analogous to capacitance, B, that is frictional coefficient, is reciprocal of resistance 1 by R, spring constant K is reciprocal of inductance 1 by L, displacement x is analogous to magnetic flux psi, and velocity V is analogous to voltage V. Now, the same concept we can utilize for torque current analogy also, that is basically applicable for rotational mechanical system. When we apply torque current analogy, then the mathematical equation for rotational mechanical system we stabilized yesterday, that is T is equal to J d 2 theta by dt 2 plus B d theta by dt plus k theta, and the nodal equation for electrical circuit we just now compiled, that is I is equal to C d 2 psi by dt 2 plus 1 by R d psi by dt plus 1 by L psi. Now, if you compare these two equations, you can say that torque is analogous to current I, moment of inertia J is analogous to capacitance, rotational frictional coefficient B is analogous to reciprocal of resistance 1 by R, torsional spring constant K is reciprocal analogous to reciprocal of inductance, that is 1 by L, Angular displacement theta is analogous to magnetic flux psi. Angular velocity omega is now analogous to voltage V. So, this is how we stabilize the analogy between mechanical and the electrical systems. Now, the elements which are in series with force voltage analogy get connected in parallel in force current analogous network. Similarly, the elements which are parallel in force voltage analogy get connected in series in force current analogous system. Now, let us try to understand how to solve the problems on analogous systems. So, what are the various steps that we can follow to solve the problem? First is the identification of all displacements due to applied force in the mechanical system. The elements, that is spring or friction and so on, which are applied between two moving surfaces will cause the change in the displacement. Now, draw the equivalent mechanical system based on node basis. So, we will rearrange the mechanical system and redraw based on the number of nodes we identify, and nodes are nothing but we see the various displacements, and based on that we will define the nodes. Then the elements which are under the same displacement will get connected in parallel under that node. Each displacement is represented by separate node. Element which is causing change in the displacement, that is maybe either friction or spring, is always between the two nodes. Then we write the equilibrium equations. At each node, the algebraic sum of all the forces acting at the node will be 0, and then we will use force voltage analogy and use the replacements of the element what we have just now discussed how to create the analogy. So, what are the analogous elements? So, analogous elements we discussed in the last class and in this session also, that force is analogous to voltage, M is analogous to inductance, the viscous friction coefficient is analogous to R, spring constant is analogous to 1 by C, x is analogous to q, x dot is analogous to I. Now, simulate the equations using loop method. The number of displacements will now be equal to number of loop currents in the electrical circuit. If you are using force current analogy, then we will use these analogous proper quantities. This is we just discussed. Force is analogous to current I, M is analogous to C, B is analogous to 1 by R, K is analogous to 1 by L, X is analogous to psi, and x dot is analogous to voltage V. Now, we convert the mechanical system into equivalent electrical circuit, and then we will solve it. In case of force current analogy, the number of displacements will be equal to number of node voltages. Now, let us try to understand what we have just now discussed with the help of one example. So, in this example we need to draw the equivalent mechanical system of the given circuit, given a mechanical system. Now, write the equilibrium equations for it and obtain the electrical analogous circuit using force voltage and force current analogy. So, if you see this figure, we have one dashpot having viscous friction coefficient B1, which is connected to M1, and force Ft is applied, and the M1 is also connected to spring K through M2 and B2 as another viscous friction coefficient, and we say that the M2 is having the displacement of x2 at any time t, and M1 is having displacement of x1 at any time t. So, now we have this mechanical system, we need to convert it into equivalent analogous electrical system. So, what we will do, the displacement of M1 we see is x1, as B1 is between M1 and the fixed support, that is the fixed support. Hence, the M1 will also be B1 is also would be under the influence of x1. So, what we can say, suppose we define two nodes, that is x1 and x2, because these are the two displacements we are seeing in the figure. For x1 we see that the force is applied to x1. So, we apply force which is causing displacement x1. So, force is now connected to x1. Then m1 and b1, these are the two elements which are under the influence of the x1 displacement. So, what we will do, we will connect both of them in parallel. So, m1 is connected now, b1 is connected, and these all three elements are now connected to node x1. Now, in case of x2, the b2 changes the displacement from x1 to x2. So, since b2 is responsible for changing the displacement from x1 to x2, so we connect b2 between x1 and x2. Now, m2 and k, these are directly under the influence of displacement x2, because k is directly connected to fixed side of the mechanical system, and then through k you are connected to m2. So, when you get the displacement in m2, m2 and k would be directly under the influence of displacement x2. So, for x2 we will connect m2 and k in parallel. So, now this mechanical system which we have now, we saw in case of the example, have been converted into equivalent node representation of the mechanical system. Now, what we will do, we will say that at node 1 and 2 your sum of the forces should be equal to 0. So, in that case, for node 1, let us write them into the Laplace domain. So, what will happen for f1, we will get the m1 d2x by dx1, d2x1 by dt2, then b1 dx1 by dt, and force. These are the three elements which you will see. So, what we will write? We will write m1 d2 x1 by dt can be represented in Laplace as s square x1, plus b1 dx1 by dt is represented as b1 s x1. Then the element which is between x1 and x2 is the dashpot b2. So, what we can write? We can write that this particular element is having the equivalent impact here, you will get, which is b2s x1 minus x2. So, you get the force applied on node 1 equal to m1 s square x1 plus b1 s x1 plus b2 s x1 minus x2, because b2 is connected between node 1 and 2. Similarly, for node 2, what you can write? In case of node 2, we do not have any external force. So, total sum of force will be 0, then it will be equal to m2 s square x2. So, if you see, you will have m2 s square x2 plus the k element you have. So, you write k x2, then again b2 s x2 minus x1, that is because of the dashpot which you have between x1 and x2. So, now you have got two mechanical equations for node 1 and node 2. Now, if you use force voltage analogy, you can simply write these two equations in the corresponding analogous voltage equations. So, what we can write? We can write Vs in place of F, we will write V, then we can write L1 S square Q1, because M1 is L1 is analogous to M1 and the X1 is analogous to Q1. So, you will write L1 S square Q1 plus R1, that is the B1 which you have. So, now here you will have R1 S Q1 plus R2 S Q1 minus Q2. So, this is what you will get when you create the analogous for first equation. Similarly, for the second equation you can write, that is 0 equal to L2 S square Q2 plus 1 upon C Q2. So, for K you will write 1 upon C plus R2 S Q2 minus Q1. Now, let us replace the Q, the value of the charge Q with Is by S, and rearrange these two equations. What we can now write, Vs is equal to L1 S I1. So, S Q1 1 S Q1 will be converted into I1. So, you have now left with L1 S I1, then R1 S Q1 will be now converted into I1. So, R1 I1 you have, then R2 as you take inside, then it will be I1 minus I2. So, you get first loop for the mesh which you will create with the help of these two equations. Similarly, for second you have 0 equal to L2 S I2 plus 1 upon S C I2 plus R2 into I2 minus I1. So, now you have two loop equations. We have used force voltage analogy. So, we will be having finally two loop equations. Now, if you convert these two equations into equivalent electrical circuit, what you can write? You can write Vs over here, then in series you will have L1. So, current I1 will be say flowing in this loop, that is loop for I1. Then from this you can easily confirm that L1 and R1 are in series. Then R2 will be common in both of the loops, that is why I1 and I2 both are coming. So, that means that R2 will be in parallel with the voltage Vs. So, then for the second loop you can see that L2 and the capacitance C are in series. So, you write L2 C and then R2 again in the common point between L1 and I1 and I2 loops. So, using these two equations you can create the equivalent electrical circuit which will represent the mechanical system which was given in the example. Now, the second case is that you can create the force current analogy also. So, in that case what you can do, you can instead of writing the equation for voltage analogous, we will write the equation for current analogous. Then we can write Is is equal to C1 S square psi 1 plus 1 by R1 S psi 1 plus 1 by R2 S psi 1 minus psi 2. Then 0 equal to C2 S square psi 2 plus 1 by L psi 2 plus 1 by R2 psi 1 by R2 S psi 2 minus psi 1. So, you have now got the two analogous equations related to the mechanical system. Now, we can replace S into psi S equal to Vs. So, for if you put these two in the above equations, you can simplify. Is is nothing but C1 S V1. So, S psi 1 will become V1. So, you get C1 S V1 plus V1 upon R1 plus 1 by R2 V1S minus V2S. Then 0 equal to 1 by R2 into V2 minus V1S plus C2 S psi 2 will become V2 C2 S V2 and then 1 by SL V2. So, now you have got two node equations which is basically can be represented with the help of this particular circuit. So, if you see here you have the C1 and R1, these are in parallel. So, C1 R1 in parallel, then you have current source I1 which is now connected to V1. Between V1 and V2 you have the resistance, that is 1 by R2. So, you will just represent with 1 by, basically this is 1 by B2 which you can compare with the mechanical system. Similarly, for the second node C2 and the L, these two are in parallel, so which you can see from here. So, in this way you can create the node analogous system where you apply instead of voltage source as a current source, and then you get the circuit which is analogous to the mechanical system which we saw in the example. Now, let us see the transfer function development for say simple liquid level system where you have some steady state flow Q which is going inside the tank, the water is flowing, and suppose there is a small change in the inflow rate from its steady state value, which will cause the small change in the head from its steady state value. So, when you change the inflow rate, the head will increase. So, now head is say example, for example you say head is now H plus small h, capital H is the steady state head before any change in the flow. Now, that will show that the capacity of the tank will increase because now flow of the water has changed. The outlet which you can control will have some resistance R. So, when you increase the inflow rate, you equivalently change the small outflow rate also. So, suppose if this is Q naught, so you will have change in inflow as well as change in outflow, which is causing change in the capacitance of the tank. Now, from the equation of capacitance of the liquid level system, we can write that the capacitance of the tank into dH by dt equal to change in flow rate, that is Q I minus Q naught, or we can write C dH is equal to Q I minus Q naught dt. Now, from the definition, what is the resistance R? That is H upon Q naught, that is change in the level difference in the tank, and then change in the flow rate, that is in meter cube per second. What is the value of C? C is nothing but change in liquid stored in the tank divided by change in head in the meter. Now, you have all those information in your hand, then you can write C dH is equal to Q I, Q naught you can replace with minus H by R dt. So, what you can write now, R C dH is equal to R Q I minus H dt, or R C dH by dt is equal to Q R I minus H, or you can say R C dH by dt plus H is equal to R Q I. Now, if you take the Laplace transform, then it will become R C dH by dt will become S H S plus the H will now become H S equal to R Q I S. Now, if you neglect the initial conditions and we want to find out the transfer function. So, for Q I as an input and H as an output, the transfer function of the system will be H by Q I. Now, if you use the previous equation, you can simply find out the value of H by Q I is nothing but R upon 1 plus S R C. So, in this way you can easily find the transfer function of the system. Now, in case instead of H you are taking Q naught as an output, and you know Q naught is nothing but H S by R. So, in that case Q naught upon Q I will become 1 upon 1 plus S R C. So, in this way the given system, that is liquid level system, can be equivalently represented with the help of the transfer functions. So, with this we can close our today's session and of course, the closure of our course. So, let us recap what we discussed in this course. So, basically we started our discussion from week 1, where we discussed about the basic circuit elements and waveforms. There we discussed what is R, L and C, and we stabilized the relationship and and found the way to calculate the value of power P. Then we studied mesh and nodal analysis. Then we discussed about the various network theorems in 2 weeks. There we discussed about the Thevenin's, Norton's maximum power transfer theorem and the superposition theorem and so on. So, these 2 weeks we devoted related to the network theorems. Then in 5th week we discussed about the first order and second order networks. Then 6th week we discussed the Laplace transform and its application. Then we used the knowledge which we acquired in the 6th week and applied the knowledge of the Laplace transform in the circuit analysis using Laplace transform in week 7. Then we discussed the 2-port network in week 8. Week 9 and 10 we focused upon the AC circuit analysis, where the network theorems which we discussed in case of DC circuit, we discussed that in view of the AC circuit, and we tried to solve few examples so that we can understand the network theorems with respect to the AC circuits. Then in week 11 we discussed about the state variable analysis, and we tried to solve couple of examples related to electrical circuit with the help of state variable analysis. And this week we discussed about the analogous system, where we stabilize the relationship between various mechanical quantities with respect to the electrical quantities. So, I hope you have enjoyed this course and you have got sufficient knowledge related to the basic electrical circuit, and I hope you will do well in your exams also. So, all the best for your exam and thank you.